Bart, please go ahead.
Thanks, Pavel. Thanks for the invitation and the opportunity to let me speak here, and thanks for all the others for joining. So I'll talk about Pearl and Jeffrey's rules in probabilistic learning. This is a topic I've been working on for a couple of years now, and I must say it's one of the most interesting topics and fascinating topics I've worked on. And I've worked on the technicalities of it, but some parts of it are still not very well understood, at least not by me. The talk will be, we'll have a big introduction where I try to informally explain the setting, and I will get to some technicalities sort of in the middle of the talk, and then get back to more general points later on. One of the interesting things that's happening today is sort of the AI revolution we're in, or you could also say the probabilistic revolution, which started maybe a couple of decades ago. And what I see as a big change in it is the move from, you could say, from Boolean reasoning to probabilistic reasoning. And this has gone with certain changes in thinking, which have been made very clear in this rather famous article, The End of Theory, which claimed we don't need theory anymore, we just need data, and we just need to find correlations in data. And that's how science will progress. It's a rather provocative article. It says we don't have to look at causality anymore. And Boolean logic is, at least that's my interpretation of it, is off. Let me start with a few basic things about correlation. You can think of a situation where studies show a strong correlation between occurrence of lung cancer and presence of ashtrays in home, and then ask a question: do ashtrays cause cancer? Of course not. There is a hidden cause in this whole situation, which has not been covered by this simple study, and it's what's called a confounding factor. It's a common source that explains the two phenomenon, and that presents the causal relation that's in here. So this is a simple answer to Anderson's claims that the correlations suffice in all these kind of things. Now, probabilistic logic is a term that exists already for a long time, but I would say it's not very well developed. And I like this quote from Judea Pearl, and I give you some time to read it yourself. And what he does in this quote is create a tension between people who work on probability theory and people who work on logic. And I think he has a point there. There is, at this stage, no well-established probabilistic logic with which you can do symbolic reasoning. And I'm thinking of logic in the terms of, like you have Boolean logic or intuitionistic logic, which come with well-established proof theories for actual reasoning. And I think that's somehow an embarrassment to the field. There are lots of, if you Google on symbolic logic, you get lots of feedback, but there is, I would say, no unity in this field. That's one of my sort of long-term goals, my points on the horizon to think about. Here's a simple example. I may think of scientists as civilized people, then I attend a conference dinner that ends in a fight. So that will lead to an update of my knowledge or my judgment about this situation. So what's happening here is, in a sense, non-monotonic reasoning. It's something I thought was true becomes less true. And I add more information, so the number of assumptions increases, but still something becomes less true. Now, this is impossible in what's called monotonic logic. And we need to handle these kind of situations to some level of non-monotonicity. And this is something most logicians immediately run away from if you raise that as a topic. But I think also we have to reason about likelihoods. So so change from Boolean value 0, 1 discrete values to 0, 1 continuous values. And that's in the field sometimes called moving from sharp to fuzzy or soft statements. And in this situation, the example says that the likelihood that scientists are civilized is decreased by events at the conference than through updating or through belief revision. This is a big topic. It's related to learning. Now, what is learning? It's the naive picture is when I teach students, I sort of fill their heads with knowledge. This picture doesn't really work, and there is in cognitive science an interesting new theory that has come up over the last, I don't know, 10, maybe 20 years. And Carl Friston at UCL is one of the proponents of this theories. And I'll describe it very, very briefly. There's a huge literature on this. So in this predictive coding theory, the way learning works is the mind is constantly making predictions. So you predict what's going to happen given your current state of knowledge. Then these predictions are compared to what actually happens in reality, and any mismatches between your predictions and what happens leads to updates in the brain. And if you read a bit of this literature, you come across phrases like the human brain is a Bayesian prediction and correction engine, which are, of course, very nice phrases in themselves. And I think there is some truth at an intuitive level to this. It often happens to me that when I hear some new theory or so, that I say to the people, to the person telling me this, let me rephrase this in my own terms and see if I got this right. So this is sort of prediction happening here, which is then compared to what's going on in reality. Now, how did I get interested in this? In the literature, there are two update rules, and this is the topic, the title also of my talk, one by Pearl and one by Jeffrey. And they have clear formulations using channels in a mathematical sense, which I'll explain later. And big questions are, what are the differences and when to use which rules? And I'll come to examples in a minute. The topic is mathematically non-trivial, as I'll explain, and especially in Jeffrey's case. And I think one of my own contributions is explaining these rules in a very precise mathematical manner. And the difference between these rules only arises when you use fuzzy statements. So if you stay, so that's essential to this world, which is not standard in probabilistic logic, and that's also possibly one reason why these rules may have or haven't got so much attention. And an intriguing question I have is, does the human mind use Pearl's rules or Jeffrey's rules? And I don't know, and I'm not scientifically equipped to answer this, but I'll have some speculations about this towards the end of my talk. Let's look at an example. This is a standard example that you see come across in Bayesian reasoning. Consider some sort of a disease that has an a priori probability of 10%. So medical people call this a prevalence of 10%. And that's a test for the disease, and the test, as is usual with tests, it has a sensitivity and a specificity. And you may have heard these terms recently in news articles, for instance, related to PCR tests with respect to COVID. So sensitivity tells you what if someone has the disease, what is the probability that the test is actually positive, so that the test is right. And let's assume it's 90%, and specificity is when someone does not have the disease, what is the chance that the test will actually be negative? And let's assume that it's 95%, which is which means that the test is pretty good. Once I've given you this data, you can, for the whole population, using this a priori probability, ask what is the probability if I test a random person that the test will be positive. You can compute this, and it's 13%. It's a bit more than 10% because there is some chance that the test will be positive anyway, even though someone does not have the test. And 90 is lower than 95. That's why this number goes up. Now, let's assume the test is performed under unfavorable circumstances, and somebody tells me, I'm 80% sure the test is positive. I'm 80% sure. I may not have seen it completely right, but I'm 80%. Now, then we can ask, what is the updated prior? What's my posterior? What is then the likelihood that this person on the test will have the disease? And now we can use two rules. We can use Pearl's rule and Jeffrey's rules. Pearl's rule will give a probability of 26% likelihood that this person has a test. If I use Jeffrey's rules, the probability is 54. And this is uncomfortable. This is uncomfortable. Both rules somehow make sense, but what is right? And there's a huge difference. And these kind of reasonings are completely common in the medical sector. And yeah, maybe next time you should ask your doctor when the test is done. Have you used Pearl or have you used Jeffrey? I'm pretty sure the doctor will look at you with a blank stare. But anyway, this is the situation. I'll show you some pictures to give a better impression. And
can I interrupt you for 1 second?
Yeah, yeah.
We have a question from David Mesto.
Okay, please go ahead.
I'll let you unmute.
Yeah, so I mean, the question is, what does 80% sure that the test is positive mean?
It's a good question. Can I postpone it?
Okay.
And because that is indeed one of the core things, issues, how to interpret that, and I'll explain the technicalities of the approach, and then we can better address this question. Let me describe the situation again. In plots, there's a priori disease probability. It was 10%. The predicted test said it's 80%. Oh, sorry, it was 13% likelihood of the disease. The observation was it's 80% sure that the disease happens. Then Pearl's update rules gives this, or was it 26? And Jeffrey gives 54 disease likelihood. And you see some big differences. What's going on here? Okay, let's go into the mathematics of all of this. Sorry, how to capture this situation. So I'll reason about distributions, and I'll use only discrete probability distributions. That suffices in this simple situation. So a distribution over set X is a formal finite sum of elements Ri xi, where the xi are the elements of the set X and the Ri are probabilities that sum up to 1. And I'm using these funny brackets, these cat brackets as they're called in quantum theory, simply to separate the probabilities from the elements. It's syntactic sugar. It has no further meaning. Now, distributions can also be described as functions from x to 0, 1 with finite support, and then the sum of these values should add up to 1. And I'll switch back and forth between this formal convex sum notation and the functional notation. The set of distributions on a set is a monad on the category of sets. It's called the distribution monad, so it's all very nice. I don't need that too much of that. A Kleisli map for such a monad, which is a function x to d of y, is also called a channel in this setting, and I'll write it in this special way as a function from x to y with a special circle on the shaft of the arrow. Such Kleisli maps can be composed, and there's a Kleisli extension operation. It's called bind or state transformation, or also prediction. And I'll use this funny notation for a push forward. So C is the channel here, and it pushes forward the state sigma on X to a state on Y. And here's a formula for this. It doesn't matter too much precisely what it is. Right now, it's just the idea that you can move a state along a channel in a forward direction. This is completely familiar in probability theory, also for people who are more familiar with continuous probability. How does it work? Let's see an example for the state and channel in the disease. Uses set D and not D for disease and not occurrence of the disease, and the test can have a positive and a negative outcome. And the prior distribution looks like, remember, we had 1/10 probability that someone has the disease, so it's 1/10 of this D and 9/10 of not the disease. And the channel is a function from D to distributions on the test. And if the disease is present, then the test has a 90% likelihood of being positive and a 10% likelihood of being negative. And if you don't have the disease, there's a 5% that the test is positive and 95% probability that the test is negative. So in this way, you can capture the prior, the prevalence, and the sensitivity and specificity via channel. And the predicted test can now be computed via this probability, and it takes this form. And remember, there was a 13.5% likelihood of a positive test a priori. And you can compute it via this state transformation along a channel. Now, there is a familiar notion of divergence between states. If I have two states, I can ask how different are they. And a common way to measure this is to use diversion, Kullback-Leibler diversion, which is abbreviated to KL, this divergence, and which has this formulation. And there are some basic results about this, that the divergence is positive and it's 0 if the two states or distributions are equal. It's not symmetric, so it's not a distance, a metric distance. That's why it's called divergence and not distance. It behaves nicely with respect to state transformation. So if I transform omega and rho along a channel C, that is non-divergence increasing. And also if I put states in parallel, I haven't explained what this is, but this can be expressed nicely with respect to this KL divergence. Okay, predicates. Let's move to logic. A predicate, as said in the beginning, will be a fuzzy function. So a predicate on the set X is a function from X to 0, 1. I see there's another question. Philip, go ahead if Powell switches on your mic.
Hi, yeah, so for divergence, could you give an example of that? What is the divergence for the example that you just gave with disease?
I'll come to that.
You'll come to that. Okay, great.
Yeah. Because divergence indeed plays an important role in this. So let me continue with the logical picture. So a predicate is a function to 0, 1, continuous, the unit interval 0, 1. And a subset forms a sharp predicate as an indicator function. So it's 1 on elements in E and 0 on elements outside E. And for an element in X, I write 1 sub X for the indicator of the singleton, which I call a point predicate. Now, given a channel C from X to Y, remember this is a probabilistic function from X to distributions on Y. And if I have a predicate Q on Y, then I can pull this back to a predicate on X. And the formula for this is like this. And this is predicate transformation from people who are more used to programming semantics, language semantics. This is weakest preconditioning, where you pull back a predicate along a computation. So state transformation goes in the forward direction, and predicate transformation goes into the backward direction. Okay, there's a bit more of logic I need. Given a state or distribution on X and a predicate on X, and I define validity, and I deliberately use this logical validity symbol for what's commonly called the expected value of the predicate in this state. And if this validity is non-zero, I define an update of the distribution, which is written here. It's omega is the distribution updated with P. As what it is, it's a normalized product of omega and P. So I multiply them and then normalize this. And in formal sum notation, it looks like this, but in functional notation, it is like this. It's the normalized product of omega and P. And if you're more used to a traditional notation, and you like to use subsets or sharp predicates, and omega, the normal notation of probability of an event, the state omega is typically left implicit, which is a bad idea. So I'll write it explicitly as the validity of the sharp, indicator predicate associated with the subset, and P, probability of event D given event E, is the validity of D in the distribution updated with E. So this makes good sense from an intuitive perspective, but I like to have this omega, this state, explicit, especially if you start moving states around with state transformation. Then a notation where the state is left implicit is a bad idea. So there are two results about validity which are useful. If I have a channel from X to Y, a state on the domain and a predicate on the codomain, I can push the state forward. So I get a state on Y and look at the validity of the predicate Q on Y there. And this validity is the same as looking in the validity in state sigma on X of the predicate Q pulled back along the channel C, and then we have a predicate on X. Okay, not very surprising. What is a very nice theorem is the following, that if I have a state distribution omega and a predicate P, and I look at the validity of omega and P and compare it to the validity of P in the distribution updated with P, then the validity of P in this updated distribution is higher than the validity in the original state omega. And I would say this is the essence of learning. By updating things, the things you update with become more true. Now, in traditional probabilistic notation, I've never seen a statement like this. And I think it's also because the notation is not suited for expressing these kind of things. The state is left implicit. So here you explicitly compare expected values in two different states, and you need to have a notation with these states explicit to be able to see these kind of very, very basic fundamental things. And so absorbing evidence P into your state makes P, the predicate P, more true. And this is a very intuitive fact that's of course at the basis of probabilistic learning, but again, not explicit. Okay, we need one more technical thing, which is the dagger of a channel. It's turning a channel around, and which corresponds to what's often called Bayesian inversion. So assume we have a channel from X to Y in a state sigma on X. What can we do? For each element small y in the of the codomain, I can form the point predicate on y, which is only true at the element y. I can transform this along the channel C and get a predicate on x. And I can use this to update my state. So update the original state that I assumed with this transform point predicate, and I get the distribution on x. So what I have now is a function from y to d of x, which is the channel turned around. And this is the dagger of this channel. It's an inversion of it. And I write it as a C dagger, but I keep the sigma explicit because it plays a role. You don't just invert the channel itself, but you need a distribution on the domain to be able to do this. And this is known from the literature. Here are some pointers, and it plays an essential role in something called disintegration in probability theory that I also worked on with former PhD student Ken Tatchell. Good. We're finally, with all this preparatory work, in a situation to formulate Pearl's and Jeffrey's updating rules. What is the setting? I have a channel from C to Y and a prior state sigma on X on the domain. And I have evidence on Y that we wish to use to update the state sigma. Now think of this if you want a cognitive picture. Sigma is what I have in my mind. The channel is how I use this to predict something in the world. So the push forward of sigma along the channel C gives a distribution on Y is my prediction given my state of Y. Now in this outside world Y, I find evidence, and this gives me a reason to update my internal state sigma in my mind. Now how to do this? There are two ways, according to Pearl and Jeffrey. And in Pearl's rule, the evidence is a predicate. And how do you update? Hopefully you can see this. I take this predicate Q, I pull it back along the channel C, giving me a predicate on X, and I can use it to update the prior state sigma, and I use this. I call this sigma of sub p for the Pearl update of sigma. Now, in Jeffrey's update rule, evidence is a distribution. It's a distribution which I call tau on y. And what is the Jeffrey update of sigma? It's I use the dagger of the channel, and then I do a push forward of this evidence. Remember, this dagger channel goes from y to x. It's turned around. And I can do a state transformation with this evidence t, which gives me a new state on x. And this is what you get out. Okay. At this stage, it's just formalized, but it's I think so. It took a bit of effort to recognize in the literature that this is what people were doing when they were applying Jeffrey's rule, because in the literature, of course, no one knows a dagger or a channel or a distribution monad. It's all formulated very concretely, but this is what's really behind this. So back to the running examples, recall that we had 80% certainty of a positive test. In Pearl's case, I translate it to a predicate Q, which is 4/5, 0.8 on P, and 1/5, 0.2 on negative test. And then the Pearl posterior is the prior updated with this pulled back predicate Q along the test channel. And this gives, if you like, you can compute this very precisely, and it gives a 20% disease likelihood. I don't understand. I think there's a typo in this sentence, so please ignore this for a moment. In Jeffrey's case, we translate the 80% certainty in this distribution, which has 80% on the positive side and 20% on the negative side. How do I compute the posterior? I take the dagger of the test channel using this prior as a state, and I do state transformation. Oh, which gives this complicated fractions, but amount to 0.45. Now there are some claims in these third points about validity and divergence, and they are part of the main results in this area. Then. So if you have a channel C from X to Y with prior state sigma, Pearl's update increases validity. And how should you read this? So remember, I had the channel C. I can push forward my state to state on Y, and I can look at the validity of Q. So this is, I predict, I have the evidence Q, and I look at how valid is this evidence. Well, if I use this evidence to update my internal state, I predict again. So I've updated my state to sigma P. I predict again with the same channel. Now the validity of Q is higher. This is what you want, right? So you learn, and your predictions become your predictions make the evidence more true. Your predictions with the updated state. What does Jeffrey do? It decreases divergence. Again, how to read this? Remember, this is my prediction. Sigma is in my mind. I predict with the channel, and tau is the evidence, and I look at how big is the divergence between the evidence tau and what I predict. Well, I can update my mind with sigma, with my mind sigma with Jeffrey's rule, predict again, and then look at the divergence between the evidence and my newly predicted state. And now this divergence is less. So the way to read this is, if I update with Jeffrey's rule, the error decreases. The error in the sense of divergence from the evidence decreases. And remember, this is what people said in prediction theory. The human mind is a Bayesian prediction and correction engine. So the prediction is here in the state transformation, and the correction is in this is in here where you reduce the divergence. Okay, the proof for Pearl is easy. I can do it on the next slide. The proof for Jeffrey is remarkably hard. It uses Galvin's spectral radius formula, which is a mathematical bazooka, and which is in the MFPS paper. Actually, I put it in the appendix of the paper because it's such a horrible, it's a 3-page proof or something. And the big question is there an easier proof? I don't have an answer to that. I said the proof of Pearl is easy. I'll try to do it. It involves a bit of symbol pushing, but I'll try to explain it. So this is the prediction in the updated Pearl state of, this is the prediction, gives me a state, and the validity of Q is the validity of, in the updated state of the transformed predicate. Oh, it's very sensitive, the mouse here. Remember, I can move the channel to the other side of the validity sign and do a pullback. Now I fill in the definition of the Pearl update, which is the sigma updated with the pullback predicates. And now remember the update validity theorem that says that if you have a predicate here on this side and you update it with it, the validity of the whole thing is bigger than before the update. So this is bigger than this. And now I can move the channel back to the other side, which gives me the predicted distribution, and I look at the validity of Q there. So in the end, I've shown that this validity, original validity, is less than the validity after the update. It's an easy proof, but again, Jeffrey's difficult. Good. Let's go back to predictive coding theory and see how we, if we can make some sense out of what has happened here. And I'll try in an informal way compare the two rules of Pearls and Jeffrey. And first look at their effect. Right? So what's the effect of Pearl's rule? Is you increase what's right. So you increase validity. And I would say as an informal psychologist, this is a way of learning. Right? You can learn by increasing what's going well. You can say to your pupils, you're doing well, improve this, go on in this direction. What Jeffrey's rule does is decrease what's going wrong. That's a different learning strategy by reducing your errors. So it also makes sense to look at learning in this way. So it's a different way. Okay, let's look at when do you learn nothing? It's of course a simple question. What kind of evidence means that you learn nothing? Now, in Pearl's case, you learn nothing from uniform evidence. So everything looks the same in the outside world. And if you update with everything is the same, nothing changes. Somehow this makes sense. You can say, if everything looks the same in the outside world, that gives me no information, so I learn nothing. When you learn nothing in Jeffrey's sense, when the evidence is exactly what you already predicted. Hey, somehow that also makes sense. If I can predict something and what I see is precisely what I predicted, okay, there's no reason for me to update, so I learn nothing. And if I compare this to the case in Pearl's rule, from Jeffrey's perspective, if everything looks the same in the outside world and I predicted something which is non-uniform, I can still learn from that. So the fact that things are uniform in the outside world is informative in a certain sense in comparison to what you predict. Okay, makes sense. Now let's look at successive updates. In Pearl's case, they commute. So if you're given two pieces of evidence, the order in which you use them for learning does not matter, which is a phenomenon which is well known in Bayesian updating. In Jeffrey's rule, they don't commute, so the order of updating does matter. Okay, so you get some non-commutativity, maybe unpleasant, well, maybe not. But these are mathematical differences. Now, what is the $1 million question? You could say, does the human mind use Pearl or Jeffrey's rule? As I said, I don't have an answer, but if you would ask me to bet, I would put my bet on Jeffrey. Still it's possible. I would say that the human mind uses Bayes in one situation and Jeffrey in another situation, or uses some convex combination of the two update rules. That's also possible in a certain way. I don't know yet. And again, I don't work in cognitive science. I can't answer this, but I would love to try and connect to people there. And I'm actually trying to talk to some of them. And why is my bet on Jeffrey? Because the human mind is extremely sensitive to the order in which information is presented. Right? The mind is very sensitive to the order of priming, is how psychologists express this. Here's my favorite example. Some of you may have seen it before, but I'm going to present you two sentences, two statements in different orders, and just think of what it does to your own mind. So the first order is as follows. The second order is this. What does it do to your mind? I mean, it's so. If you haven't seen this before, it gives an amazingly different view on Bob. So in the first case, you may say, "Well, Bob is a nice guy," and well, maybe in the second case, he's a nice guy too, but you can also interpret this in a different way. And it's a strong, convincing example. Okay, let me come to conclusions, given time. updating is one of the magical things in probabilistic logic. It's a pillar of the AI revolution, you could say. But I would say from a logical perspective, it's poorly understood. Two update rules, they're poorly understood when to use which one. I must say I've talked to several of my colleagues who work in AI or in data science and big data analytics, and I've confronted them with the differences. And I said, what's going on? Can you explain this to me? And what should I use? And in general, they get rather uncomfortable about this whole thing. They say, no, you've made a mistake. You must have made a mistake. And then I explain again, oh, yeah, but you use fuzzy predicates. We don't do this. Yeah, but okay, let's assume you do use fuzzy predicates. Yeah, maybe you shouldn't do this. Anyway, I do think there is a serious issue going on, and I find it an interesting challenge to think about this. So again, where am I on this slide? The Dyer paper formulates the two rules in a very clear form. At the time, I did not have this precise difference between increasing validity and decreasing divergence. That came later. It should have been in the same paper, but progress is slow. And so MFPS has the mathematical result, especially that Jeffrey decreases divergence. And you could say, well, maybe Pearl also decreases divergence. That's not the case. That's not the case. There are examples, and they're in the MFPS paper, or you can look them up, and where Jeffrey does not increase validity. So there are a possible future work is to extend this to continuous or even quantum settings. And I'm very much interested to look at the connection to the cognition, to what's going on in cognition theory. Other possible experiments that one can think of that could shed some light on what the mind does in these kind of cases. I have no idea. So if you have some connections there, that would be nice. This is it. I think it's 45 minutes, rather precisely. Thanks for attention. I'm happy to take more questions.
Thank you very much, Bart. I'm just going to ask everybody to unmute themselves, and let's give Bart a round of applause.
Thanks.
Okay, so can everyone just mute themselves again, and please put your hand up if you would like to ask a question. We've got plenty of time for questions. David, go ahead.
Yeah, so I asked earlier what you meant by 80% sure it's positive, and you said you were going to answer later, but you didn't.
Yeah. No, I was aware of it.
It's kind of quite key to the whole thing.
Yeah. What does 80% certainty mean? Was your question? Now, as you may have noticed in the Pearl update rule, I translated the evidence to a predicate, and in the Jeffrey case, I translated it to a distribution. The Jeffrey answer, I think, can best be understood as in a frequentist manner. So that means 80% sure of a positive test would be that in 4 out of 5 cases, I would think it's a positive test, and 1 out of 5 not. And what you actually do in Jeffrey's rule, you take the point updates, positive tests and negative tests, and you take 80% positive and 20% of the updates negative, and that's how the rule works. So it's a sort of frequentist interpretation. In the Pearlian sense, you use a predicate for the 80% sure, and I think the best way to understand it is in terms of applying sensitivity and specificity to yourself as an observer. I remember I used these terms to describe how good the test is, but you can apply this to yourself also. If I really see a positive test, what is the likelihood that I also report it? And if I see a negative test, what's the likelihood I report a negative test? So that's one way of interpreting it, and that's how I look at it. But again, it's a non-mathematical interpretation, and I'm not sure if there is a precise mathematical answer to your question, but hopefully this helps a bit, and I'm happy to hear what you think of it.
Yeah, I mean, I guess especially the first one you said, Jeff. Well, I mean, I agree. And what my question was kind of getting at is, it doesn't seem to me that 80% sure it's positive is likely to be very meaningful at all, unless you specify type 1 and type 2 error. I mean,
yeah, I agree. I've glossed over this, but it may help to get more clarity on where to use which interpretation. Thanks. So there were other questions.
A question from Barbara. Yeah, Barbara, please go ahead.
Okay, so thanks a lot for the nice talk. I have a question. I mean, there might be other update rules besides Pearl's and Jeffrey's update rules. There could be others. And then what you maybe want is that Pearl's update rule increases validity. And of all update rules that do increase validity, it is somehow the best one, or the most canonical one, or the most general one. And similar for Jeffrey, for all the update rules that decrease divergence, it's kind of the best one. Do you have some result like this in mind, or do you think something like this can be done?
No, but we would first have to agree on a specification of what is an update rule. And I don't know what that is. I don't know what that is yet. So I'm bouncing it back. But it could be indeed that these two rules are sort of best in their class. Further research question. Yeah.
Okay, thanks.
We have Dexter next. Dexter, go ahead.
Hi, very nice talk, Bart. Thank you.
Thanks.
There's a huge problem in the world right now with misinformation. And it occurs to me that this theory may have something to say about that. If you have a lot of people that live in an echo chamber and are reinforcing each other with misinformation, they begin to believe that the world works in a certain way. And it seems to me that getting out of that echo chamber is one way to solve it. And it occurs to me that that this theory might actually give you a way to do that, or at least a way of measuring any technique that might purport to do that. And I'm wondering if you've thought about that at all.
I've been thinking about misinformation, and disinformation, but to be honest, nothing in relation to this, these rules. But I see your point. And I think it might be interesting. What it reminds me of is some of the people who have, some people who have looked at the difference between these rules. There are a few publications in the literature on this. And if you go to my Gyre publication, you can see them. And some people who thought about this are from economics. And I elaborated also one of their examples in the paper. They also don't have a good explanation about when to use Pearl or Jeffrey. But what they say is you should use Jeffrey in case you're confronted with a surprise. So when you have surprising information, which sort of goes counter to what you're saying. And you could, I'm speculating now, you could say Pearl's rule is an echo chamber rule. It increases what you've been thinking already, and it's a confirmation bias rule. And Jeffrey presents you with, confronts you with something, and confronts you, which is different from what you already thought, and leads to a different kind of update where you think, oh, I've been wrong all the time. I should do something. So Going along, marching along these speculation, you would say indeed Pearl is inside an echo chamber and Jeffrey is a way to get out of it.
Yeah, and I think another piece of evidence for that is when you consider people growing up in a small town and their world is very uniform. And when they go to college, say, or they go to move to a different town, they discover that there are different people who think differently, and it kind of increases the entropy of their distribution. And that seems to point to Jeffrey.
Yeah.
Yeah. Do you?
Very interesting thought, Dexter. I'm open to thinking more about this.
All right. Thank you.
Yeah, let's if possible, keep a conversation open on this.
All right.
Filippo is next. Filippo, go ahead.
Yes, thanks a lot, Bart, for the wonderful talk. I was wondering about this divergence measure, which you said is not symmetric. But I don't understand why you use the evidence tau as a first argument, and then the updated the state and the updated state. I mean, does it work even if you switch the argument, or?
Let me try.
Here.
Yeah, here.
Next, I think is next.
And but here is the definition of Jeffrey's rule.
No, I mean the inequality, the main.
Ah, okay. You didn't understand this inequality.
I mean, no, I understand. I don't understand why you put the evidence tau. I mean, this is not symmetric, right? This divergence.
Yeah,
so...
yeah. That's subtle. I think it also works the other way around, but this way I could prove it. I mean, it worked. Yeah, there has some very subtle things here. I can't put my finger on it precisely.
Okay.
Yeah, but indeed, I think it works in both directions. But the proof was so difficult that when I finished it in one direction, I was happy and I gave up and didn't want to think about the option possibility.
Okay.
There's a remote possibility that the proof might be easy if you turn them around. That would be a bit of a shock to me. But yeah.
Okay. No, because I mean, being not symmetric, it's a bit weird to me in this.
Yeah,
this context.
It is, but Kullback-Leib divergence is absolutely standard. It's all over the place in probability theory.
Okay.
Yeah.
Okay. Thank you very much.
Yeah.
Okay, Michael, please go ahead.
Yeah. Thanks for your.
Can you speak up a bit? You're very soft.
Okay. Maybe I also should make sure I have correct settings. Thanks for your talk. And I have the following question that you have defined the Pearl and Jerry update rules. And for example, do I understand correctly that at least for the Pearl update rules, it's actually the standard Bayesian update?
Yeah.
But given that we have this experiment which gives us 80% in both directions, 80% error in both directions. And Jeffrey is basically a Bayesian update also, but here we have a different experiment. Our experiment is defined in terms of our current a posteriori expectations. Our experiment is defined in terms that we expect that 80% of our acceptance corresponds to positive test based on our current knowledge of the distribution of the tests.
Yeah, that's true. Indeed, I can add 2 refinements to this. So in the framework of Pearl, so Pearl does not explicitly talk about predicates, fuzzy predicates, but he does it implicitly. So when he talks about his networks and predicates in there, he adds an extra table, an extra channel, I would say, to the network, a channel going to 2. And then if you update via this channel using a point predicate at 2, truth and at 2, then the predicate transformation is actually a fuzzy predicate. So it's in there, but not made explicit. That's my first remark. The second one is about Jeffrey rules. So Jeffrey's rule occurs mostly in the literature, where the channel that you use to see is a so-called deterministic channel. And deterministic channel is simply a function. And it's a special property that if you have such a function, the Jeffrey update precisely gives you the evidence distribution. So it has often been described in the literatures like you do. So you adapt your internal state so that you precisely get the posterior as your prediction, the tau as your prediction. I think that's what you were trying to say earlier. But so what I've done is formulate Jeffrey's rule for channels more generally, and then this equality disappears and had to be replaced by this divergence statement.
But I mean, basically my real question is that if these are just Bayesian update rules for very different measurement procedures, for very different interpretations of this 80%, as has been already discussed in the question by, I think, David, that if it is just Bayesian updates for two different very different experiments, then the question which one to use is basically which kind of experiments we do more often, right?
Yep. Yep. But I have nothing else to say to add to this.
Because yeah, intuitive, I would say that it's probably easy, like, okay, it definitely explains the commutativity, non-commutativity case for trivial reasons, because the Pearl experiments are not dependent on our knowledge, and Jeffrey experiments are. And yeah, I would say it's probably easier to ensure that your experiment is good in the Pearl sense than in the Jeffrey sense. Okay, yeah. Easy,
Okay.
thank you.
Thanks.
Okay, so we have a couple more questions. Tano, please go ahead and unmute.
Thank you for the talk, and I have a somewhat different question than before. The ones when you speak about predicates, you say they are fuzzy / soft, right? And what do you mostly mean? Do you mean this in the sense that you have some confidence that predicate holds, or more in the sense of fuzzy logic, that it's a measure of how strong it is? And these are somewhat different but related issues. And could this somehow be related to the question of being Jeffrey or Pearl type?
So what again is the difference between your two interpretations of a soft predicate? So one is fuzzy and the other?
Is, let's say, probabilistic. You consider confidence that something holds.
Yeah, I would say it's related to confidence level indeed. So I'm 80% sure that in my sensitivity or specificity is such and such.
So that when you say fuzzy, you mean probabilistic fuzzy, but not fuzzy in the sense of fuzzy logic, right?
Yeah, I don't know precisely what that means. I mean fuzzy in a technical sense, as simply as having a codomain unit in the val 01 for your predicates.
Okay, that made it clear. Thank you.
Yeah, okay.
Okay, I think we've run out of questions unless there's someone who wants to jump in right at the end. So that was a very fascinating question and answer session. So I'll ask everyone to unmute once again, and we can give Bart one other round of applause, and I'll stop the recording.